Compute the indicated matrices if possible. Now we have three parts here. So in part A, we want to find the product of matrix A with the transpose of matrix C. So we can see that matrix A is a 2 by 2 matrix. And to find the transpose of matrix C, we need to interchange the rows and columns, which is producing a 2 by 3 matrix. So since the number of columns of matrix A is equal to the number of rows of the transpose of matrix C, the product exists. So giving ourselves a little bit more room, we are officially ready to compute this product. So we have matrix A multiplied by the transpose of matrix C, and we're going to use the row-column rule of matrix multiplication to find this product. So here we go. We have the first row of A times the first column of C transpose, which gives us 2 plus 5. We have the first row of A times the second column of C transpose, which gives us 0 plus 15. And the first row of A times the third column of A transpose leaves us with 1 plus 10. Now we have the second row of A times the first column of C transpose, which gives us 0 plus 2. We have the second row of A times the second column of C transpose, giving us 0 plus 6. And the second row of A times the third column of C transpose, giving us 0 plus 4. And simplifying, we are left with the 2 by 3 matrix, 7, 15, 11, 2, 6, 4. So there you have it. This is the product of matrix A with C transpose. Now in part B, we are asked to compute matrix B times matrix C plus matrix A. So looking at matrices B and C first, we see that matrix B is a 2 by 3 matrix, and matrix C is a 3 by 2 matrix. So since the number of columns in the first matrix matches the number of rows in the second matrix, the product exists. And we will use, again, the row-column rule for matrix multiplication to compute this product. So here we go. We have the first row of B times the first column of C, which gives us -2 plus 0 minus 5. We have the first row of B times the second column of C, which gives us 1 plus 9 plus 10. Now we have the second row of B times the first column of C, giving us -4 plus 0 minus 6. And the second row of B times the second column of C gives us 2 plus 12 plus 12. And simplifying, we are left with the 2 by 2 matrix, -7, 20, -10, 26. So notice that the product of matrix B and matrix C produces a 2 by 2 matrix, which is the same size as matrix A. So this lets us know that we can continue and find the sum of the product B times C plus matrix A. So taking that cute 2 by 2 matrix we just found above and adding this to the given matrix A, to find this sum, we simply need to combine up the like terms. So we have -7 minus 1 gives us -8. 20 plus 5 gives us 25. -10 plus 0 is -10. And 26 plus 2 is 28. Making this our beautiful final answer. Now in part C, we are asked to find the inverse of the 2 by 2 matrix A. Now, keeping the definition of a 2 by 2 inverse in mind, the first thing that we want to do is find the determinant of matrix A to verify that it's invertible. So letting our given 2 by 2 matrix A be defined as A, B, C, D, we have the determinant of A is equal to -1 multiplied by 2 minus 0 multiplied by 5. So we have -2 minus 0 leaves us with -2, which we can see does not equal 0, and therefore A is invertible. So we can say that A inverse is going to be equal to 1 by -2 multiplied by the 2 by 2 matrix 2, -5, 0, minus 1. And now distributing that scalar multiple of -1/2 through, we are left with 2 divided by -2 leaves us with -1. -5 divided by -2 leaves us with 5/2. 0 divided by -2 is 0. And then -1 divided by -2 leaves us with +1/2. So there you have it. The inverse of matrix A is the 2 by 2 matrix, -1, 5/2, 0, 1/2.